Example, we've actually got two things, looks like circles again, but unfortunately we're going to have to use the algebraic method here because it doesn't break down so nicely into two different circles. And the reason for that is you've actually got the circles tied up with each other. You've got this kind of expression if I put everything onto the left side of the equation. So we're going to make a substitution, let z equal x plus iy. Remember, this is the nice substitution to make if you're dealing with graphs. We always just use x and y instead of a and b. And then all we have to do is substitute in. Now the other thing that you need to remember as well is that the modulus of z is equal to the square root of the real part squared plus, the imaginary part squared, like that. So let's look at the two parts here. We've got mod of z plus 1, modulus of z plus 3. So I'm going to do a substitution. I'm just looking at the two parts separately, so I'm looking at the two modulus parts separately. Okay, I've done my substitution. I'm now going to look at the real parts. They're the real parts, and the imaginary parts squared. So the real part squared would be x plus 3 all squared. The imaginary part, I'll do this in green, is 1 squared, and it's 1 times y squared, because that's the imaginary part here with the I. Okay, so we have that. The other equation that we have here is the 2 and the z minus I. Let's look at the mod z minus I. That's going to be, let's make the same substitution, x plus iy minus I this time equals the square root, and the real part here is the x, so it's just x squared. The imaginary part, there's actually two imaginary parts here, the y, and there's a minus 1. So it's going to be y minus 1 and all of that squared. The imaginary part squared, and in light blue, the real part squared. Okay, so we've got those two pieces now. What I'm going to do is I'm going to look at what we start with. We've got that. And let's actually substitute what we found now. So the modulus of z plus 3 is the square root of x plus 3 all squared, plus y squared, which equals 2. And this modulus of z minus I is the square root of x squared plus y take 1 squared. Now the reason that I've got this set up this way is if we square both sides, we can get rid of the square root, which is what you want to do. It's awful having that square root there. Let's square both sides, get rid of it. So squaring both sides, we're going to be left with what's underneath the square root. Here, the 2 will be squared, so it will be 2 squared outside of everything that was underneath the square root. And I'll just use big square brackets there. Okay, so we've got that. So we've got x plus 3 all squared plus y squared equals 4 outside of x squared plus y take 1 all squared, like that. That's where we are at this point. Now it's a good idea here to expand things. Okay, so expand out the x plus 3 and the y take away 1. So I'm just going to write this out with both brackets. You can do this in your head. Just for me, just for the working here. And we've got 4x squared, just going to put the 4 through, plus 4. And y take 1 squared is the y take 1 with the both brackets written out like that. This makes it nice to see now you've got x squared plus, this is going to be 6x plus 9 plus y squared equals, and we've got on the right hand side 4x squared plus 4 outside of, this is y squared, it'll be 2, take away 2y plus 1. Nearly done. X squared plus 6x plus 9 plus y squared equals 4x squared plus 4y squared minus 8y. I'm just expanding this. Okay. Plus 4. And now what we're going to do is put everything onto the left hand side. So you want to just simplify things a little bit, and I'll do this with blue. So we're going to have, I might actually take, just looking at this will be easier if I take this stuff all over to the other side. So I'll have 4x squared plus 4y squared minus 8y plus 4. Take all of this away. So take away x squared, take away 6x, take away 9, and take away y squared equals 0. So simplifying, we've got 3x squared, and we've got plus 3y squared. We've got minus 14, we've got minus 8y, minus 6x, and minus 5 equals 0. Okay, now that's really okay in terms of what we're working with there. So we would have to do, again, this is a bit of a completing the square exercise here, collecting together the x stuff and the y stuff and then working with that. To complete the square with this now, you could straight up put that into your graphing calculator and actually graph this. You would hopefully recognize that that's got the look of a circle, which is in the standard form, so you could graph that. We've done that before with the CAS, but I'm going to complete the square just as a bit of revision for how you'd actually get your final equation here. So you could pause the video at this point, you can try and do this now without me. I'll do it in blue. So we're going to put the x's together and put the y's together, so 3x squared minus 6x plus 3y squared minus 8y equals 5. I'm just putting the 5 onto the other side. Now that we've got our x's and our y's together, what we're going to do here, I'm going to factor the 3 outside of the x's, so I've got that, and I'll factor the 3 outside of the y's as well, which looks a bit ugly, unfortunately. And what I'm going to do at this point now is I'm going to complete the square with these expressions. So you can see now that completing the square is a massive part of complex number. You do it all the time, so it's really good to get really good at it. So it's pretty quick. So here, the second coefficient, it's -2, so halve it, it's 1, square it, it's 1, add it, and subtract it. And here, I'm just using square brackets. 8 over 3, half of 8 over 3 is 8 over 6. And then if we square the top and the bottom, we're going to get 64 over 36. So this is going to be plus 64 over 36 minus 64 over 36 equals 5. And again here, remember that the first 3 terms should always be a perfect square. So those terms that are underlined there in green. So we've got 3 outside of this is x minus 1 all squared. This one here is not as nice. It's the square root of 64, which is 8, and the square root of 36 is 6. And it's a minus because of that second sign there. And minus 64 over 36 equals 5. And we're just going to now expand out. So expand the 3, so it multiplies both the terms in those square brackets. So we've now got 3 outside of x minus 1 squared minus 3. And we've got 3 of y outside of, I'm going to simplify this actually, divide the top and the bottom by 2. And here we've got 64 over 36 times 3. And we know that we could divide both of these by 3 to get 12 underneath there. So we're nearly done. I'm just going to put the parts together here where we've got squared parts, so the 3 and the y minus 4/3 squared. Okay, this minus 3 I'm actually going to put over to the other side as a plus. And this equation that I've got here, I've got 64 over 12, and I could divide the top, and the bottom there. So we get, pen's changed. So we get there, divide the top and the bottom by 4, so we've got 16 and 3, so 16 over 3. And I'm just going to rewrite this, that's 8 plus 16 over 3, which is 24 over 3 plus 16 over 3, which is 40 over 3. So I'm just working through there. You can do that with your calculator, of course. So what we've got now, so far, and we're nearly there, which is exciting, because it's a long question. We've got 2 squared factors equals 40 over 3. Let's divide both sides by 3. And the reason I want to do that is because I'd like to get rid of those coefficients in front of the squared parts so that I end up with something that looks like a graph that I recognise. So if we get rid of those 3's out the front and take them to the other side, divide underneath. What we can see here is that our graph actually becomes clear now, and it's this is our locus or graph, and the graph or locus is a circle. Okay. Now the circle that you're looking at here has been translated. It's not an ellipse because it's not divided by different things here, but it's a circle with a centre at 1/4. Remember, opposite signs to what's in the brackets, and a radius or radius squared of 40 on 9, or a radius of root 40 over 9, which is 2 root 10 over 9 for the radius. So after all of that work, what we found is that our original graph, finding the locus defined by this, actually ended up being, at the end of the day, a circle. Okay. Now a nice result that actually is in your textbook, and I'll put this just on this page here in red. It's something to write at the end of your notes there, which is a very important thing, is that for A and B that are complex, that's a C, and a K that is an element of R plus, so that's all the integers except for, all the positive integers except for 0, and it says excluding 1, so that would be 2, 3, 4, and R plus also includes all real things, so all the fractions and all the irrational numbers as well. So it can include, and I should really, everything as long as you're not including 1. So provided that that's satisfied, any equations that are written as z minus a, modulus of that, equals k of z minus b, will always be a circle. So you can actually see that this equation here satisfies this expression. So a and b are both real numbers, and I'm just rewriting this, it's a bit neater. A and b are both real numbers here, okay? And you can see, complex numbers, excuse me, so 3 and the I, and you can see as well that you've got a number out the front here, which is a 2. And because 2 is any of the real plus excluding 1, that's cool, it's bigger than 1, you can see that this expression should give you a circle. And we found by doing the algebra that, yeah, after all that algebra, we did in fact get a circle. A really ugly looking circle, but we did get a circle. So that's how you define the locus for this particular equation.